guys, we're still discussing subtopic 1.3 electric potential. We continue with point E, deduce the change in potential energy, which is delta U, between 2 points in electric field, and F, calculate the potential energy of the system of points. So let us look our notes from point E. Where is it? Okay, here. Point E, deduce the change in potential energy or delta U between 2 points in electric field. Before we understand the change in the potential energy, we need to understand the electric potential energy. There's a difference between these 2 points. We are going to discuss or deduce the change in the potential energy. The change in potential energy. Change. So, before we go to understand the change in the potential energy, we need to understand first the electric potential energy. What is the electric potential energy? The electric potential energy U of a charge Q, let's say this is a charge Q, at a point in an electric field where the point charge Q at point A have a distance of R from charge Q. So to calculate the electric potential energy at point A or at charge at point A, we need to use formula U equal to QV. What is Q? Q is a charge at point A and V is a electric potential at point A. We also can calculate the electric potential energy U by substituting V equal to KQ, capital Q, K capital Q over R. So we will gain the formula of here. Energy, electric potential energy can be calculated by using this formula, which is KQ at point A and capital Q, which is isolated charge, over the distance between charge capital Q and charge at point A. This electric potential energy is a scalar quantity and the unit is in joule, and the sign of the charge must be substituted in the calculation. Okay, let's say we want to calculate the energy at a charge Q at point A. So if the charge at point A is a negative charge, or let's say it is electron, so we must put the sign negative. If it's a positive charge, then we add it as positive sign. Let us see this exercise. What is the potential energy? What is the potential energy of electron? That is 0.53 exponent negative 10 meter from a proton. So by using this formula, U equal to, which is K is a electrostatic constant or Coulomb constant. If we refer to the constant value, which have 9 exponent 10 to the power of 9, and a small charge Q is an electron which have negative 1.6 exponent negative 19 multiplied by capital Q, which is positive charge, also have the same magnitude, but it is a positive sign, which is 1.6 times 10 to the power of 19, negative 19, sorry, over R is a distance between that two charge, electron and proton, is 0.53 times with 10 to the power of negative 10. So let's find the answer. You must get the answer, negative 4.35 exponent negative 18 joule. Don't forget unit. Unit is joule. Now, after we understand to calculate or to find the electric potential energy, then we can discuss the change. Discuss the change in electric potential energy, which is, let's say, we have 2 points, point A and point B. Both points have their own energy. So to find the change in electric potential energy, we can write the formula as, delta U equal to UAB. It shows the change, the change in electric potential energy. This symbol, triangle, is a change, the symbol for change in electric potential energy between point A and B. So we need to calculate energy at point B first, minus with energy at point A. Okay, as we know, U equal to QVB. U for B equal to QV for B, and U for A, or electric potential energy at point A, equal to charge at point A, Q, multiplied by electric potential at point A. So it's like we need to find the charge at point A and also charge at point B. Okay, then we need to calculate U. We need to calculate U at point A and U at point B. Okay, then after that we substitute, we subtract between point A, energy at point B, with energy at point A. So we can write this equation UAB equal to QVAB. And don't forget, from slide 10 above, under the topic of potential difference, we have work done to bring a charge from point A to point B is equal to QVAB. From these two equations, we can find that it has the same, which is Q equation 1 equal to equation 2. So we can write it as UAB equal to WAB, mean energy. Yeah? The difference between electric potential energy at point A and the electric potential energy at point B is equal to, if we find the difference, or if we find the change of electric potential energy at point A and point B is equal to the work done to move or to bring a charge, a charge Q from point A to point B. Let us see example 1.3.5. A. What is the electric potential energy of a charge 0.05 microcoulomb at a point 10 centimeter first, and then to 50 centimeter from a point charge of 2 microcoulomb. Okay, so there is two charge here, which is 0.05 microcoulomb and 2 microcoulomb. The first one, the distance between two charge is 10 cm, then the second one is 50 centimeter. So how do we calculate the energy for the A1, which is 10 centimeter between these 2 point charge? So by substituting or by using the formula here, U equal to QKQ over R, or we can write it as KQ minus Q multiplied by capital Q over R. Okay, sorry, K small q multiplied by capital Q over R. So we substitute the value of K with 9 exponent 9. We substitute the first charge with 0.05 micro, convert into SI unit, so it is exponent negative 6, and also the other one is 2 microcoulomb, which is 2 exponent negative 5, and distance between it is 10 exponent negative 2. So we have the answer is 9 exponent negative 3 joule. Okay, the second one, we just substitute or change the distance between it is 50 exponent negative 2 meter. So we have the other the second answer, 1.8 exponent negative 3 joule. All right, try to calculate this to your calculator. Is it the answer is correct or not? Then we go to B, find the change in the electric potential energy between 1 and 2. So change in electric potential energy, as we discussed before, can write as here. Okay, the change of electric potential energy equal to the energy at 0.10 cm minus with energy at 15 cm. Alright, the first one is 10 cm minus with the second one. Okay, so we have the answer. Substitute the value for energy at 10 between the charge is 10 cm and substitute with energy with 50 cm. So we have the answer here. Okay, you can try to calculate it whether the answer is correct or not. Now we go to point F. Calculate the potential energy of the system of point charge. Okay, how do we calculate this? Electrical potential energy of a system of point charge. This is a system mean that we have more than two charge, or more than that, maybe 3, 4 and more. Okay, consider the system with 3-point charge. We have charge Q1, Q2 and Q3. So to calculate the potential energy of this system, okay, we just adding all the energy, okay, and we got the answer. The electric potential, let us read this point. The electric potential energy of the system of charge is the work done to move or to bring all the charge from the infinity to the point where the charge is placed. Alright, this is how we calculate the potential energy of the system. Don't confuse with the point E here. Point E is about the change in electric potential between 2 points. Okay? The first point A have energy. Point B also have their own energy. So we calculate the change or the difference between 2 points. Here is to find the total energy of a system of point charge. This is an example. Example 1.3.6. We have 3 charges, Q1, which is negative 10 microcoulomb, Q2, which is 10 microcoulomb, and Q3 also 10 microcoulomb. So the distance between Q1 and Q3 is 4 cm. We label it as R12. The distance between Q2 and Q3 is 5 cm, and the distance between Q3 and Q1 is 5 cm also. So to calculate this, we just sum up all the energy from point charge Q1, Q2, adding with energy Q1 and Q2, and plus with energy from Q2 and Q3 by using a formula as we learned before, which is U equal to KQ1 Q2 over R 1 2 here. This is for 1 2, this is for 1 3, and this is for 2 3. Substitute the value, then we got the answer, which is negative 22.5 Joule. Right now we go to the last subtopic, 1.4, charge in a uniform electric field. It consists of 2 points. The first one, A, explain quantitatively with the aid of a diagram the motion of the charge in a uniform electric field, and number B is use the formula electric field in a uniform electric field, which is E equal to V, which is electric potential, over D, which is distance between two plates for uniform electric field. Okay, if we have the parallel plate between this plate, negative plate, and the positive plate, where V is a potential difference between these two plates and D is a distance between these two plates. So to calculate the electric potential, to calculate the electric field between these two plates, we use the formula E equal to V over, I repeat again, to calculate the electric field between these two parallel plates, we have by using the formula V over D. The unit for this electric field is volt per meter, and it is a vector quantity, always directed from positive charge to the negative, always directed from the positive plate to the negative plate. Alright, now to explain the quantitatively with the aid of diagram the motion of the charge in a uniform electric field, here is we are going to discuss in four cases. Okay, for the case 1, it is a stationary charge in a uniform electric field at figure A here, and we combine it with a case 4 in figure B, which is charge in dynamic equilibrium. Case 1, stationary charge, means that the charge is in static in a uniform electric field. For case 4, charge in dynamic equilibrium, means that the charge moves through the uniform electric field with constant velocity. Okay, let us read here. Figure A and B shows a particle with positive charge Q is held stationary, and the other one is figure B, move at constant speed respectively in a uniform electric field. The force act on the particle are electrostatic force, which is directed upward, and a weight which is directed downward. For the particle in the static equilibrium, like figure A, and dynamic equilibrium, which move horizontally in straight line like figure B, the electric force equal to weight. Okay, so the electrostatic force we see here, the charge which in the uniform electric field is a positive charge, will attract to the plate negative plate with force Fe. So due to the figure B, the charge is a positive charge and it will attract to the negative plate with electric force upward. At the same time, both charges, figure A and figure B, have a weight which directed downward. So, if the charge doesn't move like figure A, it means that the charge have the force act on that charge is only electric force which is equal to weight W. Same to figure B, the charge move in horizontally, so that means the electrostatic force have the same quantity with the weight is directed downward. So we continue with the case 3. Case 3 different with the case 1 and case 4. Case 4, if we look at the diagram of figure B, it moves perpendicular with the direction of electric field. In case 3, the charge will move parallel with the direction of the electric field. For case 3A, which parallel plate vertically with each other, okay, mean that the charge will move horizontally. If this happens, the force due to the electrostatic force, which is F electric, will equal to ma. So we substitute the electrostatic force with Q equal to ma. Then we have A equal to Q E over M.